Good afternoon. One of the things we've always talked about is we look at a lot of the topics that we've covered in the past day and a half and realize that we're solving a lot of the big problems, but nobody's ever there to solve the little problems, the problems that you don't really know that you have. Which is the right button? That's the one. Okay, cool. So we always know there's tools to solve the big problems, but how do you solve the little problems? And I categorize problems as there's two. The two types of problems. There's the ones like, I know what I need, how do I fix it? And as opposed to, I don't know what I need, how do I get past this issue? So if I know what I need, hey, I need to create a list, I need to create vectors, I need some I/O and all that stuff. We know there's standard libraries, reusable source. I can go ask Stack Overflow how to solve this problem, those type of things. Those are easy. I know the questions that I need to ask so I can find an answer. If I don't know the question I need to ask, my code isn't working, how come? What's the best way to write this type of code? Those are the things that, if you ask Google that kind of question, you're not really going to get a specific answer. And other thing, issues about the language. Hey, I've been using Ada forever, but I haven't tried any of the new 2012 stuff, any things like that. How do I use that? Now you can obviously read a reference manual, but how do I actually use some of those techniques? So these are the type of problems that we always see. Has anyone seen this one before? I actually showed that when I demonstrated my slides, the person I demonstrated to didn't understand the problem in this slide. Does anyone see this? I'm looking at my code. What's wrong with my code? It doesn't work. Does anyone know what the problem is? Somebody? Two does. The mind just starts reading it. You say the and the. So if you haven't seen that and you say, hey, you know what, I read that, I didn't see that. And that's the type of thing when you look at your own code and try to figure out why it doesn't work, it's your code, it does what it's supposed to, why is it failing? Different type of problem. Where's the red dot? In the box or outside the box? Can't tell. You don't have enough information to solve this problem. This is a different one. Anyone know this one? Haven't seen this one? Which direction is the bus going?
Going to the left.
Towards the left. Why?
This is going on the right.
Right. The one where it's explained to me is kids, elementary school kids understand this one. They know it's going to the left because they have extra information that you as an adult tend not to use, knowing that the door is on the other side. Of course, I showed it to a Frenchman and he said, well, maybe it's an English bus and it's going to the right. Sorry, no. So once someone points these things out, as soon as you sit and say, hey, the door's on the other side, people understand, yes, now I understand. So now I know if I get the right question, if I know have the right question, the phrasing of the question, I can get the right answer. So when I need those questions, where do I go? Where do I personally go? Where do you go? Where do people go in generally? Typically when you write code, you've got two solid bases of information. What you've done in the past and what's currently out there, either in your code already or somewhere out on the web, GitHub, SourceForge, or whatever. So my thing, most of us have done this thing, I don't know how to do this, let me find somebody who does something like that, and then I'll copy it, duplicate it, and assume it works. If I can't find that duplication, how do I solve that particular problem? And hopefully the next few slides are going to give you an idea of some of the ways to solve problems you didn't know that were actually problems. So I'm just going to cover each one of these topics, dealing with the language itself, how to write your code, and a little bit of debugging techniques. Typically, this is someone pointed out to me, we always look at floating point. Everyone writes code, they write floating point numbers and all that type of stuff. Floating point numbers in an embedded system can be expensive. You're either using an FPU, you're using some help, you're simulating it in software. Floating point numbers are expensive. Ada has this concept called fixed point types. And a fixed point type is just as valid as floating point numbers. It doesn't necessarily have the same range because you're limited by the size of words, but it allows you to approximate decimals better using binary representation. This is a typical fixed point number here, delta 1. The default behavior of a fixed point number is to use binary representation, powers of 2. So if I have this number here, -1 to 1, I find a power of 2 that's smaller than, that allows me to get to that smallest delta. 1/16 is going to be smaller than that, and now I can measure it by powers of 2. Very helpful. And now I've got this decimal number, this floating point number that's represented in pure binary. Obviously, if I don't want these fractions in here, if I want, really I need this delta, you can actually tell the language like how to use that delta. So now it's still using binary numbers, but now the binary numbers, the binary representation, instead of mantis and exponent and all that stuff, it's using each bit to represent, each bit is going to represent 1/100th. So however many bits you get that range allowed. One of the other categories of issues is there's a benefit in Ada. We always talk about strong typing. Strong typing is awesome. Okay? Distance plus time, that's a compile error. It's not just causes your satellite to crash into the earth or whatever. But it makes math different. Distance plus time is a compile error, but distance divided by, I said that wrong, yeah. Distance divided by time is speed. That's a valid calculation, and how do I generate that? So we would always write multiplication factors. We can have speed or whatever here. We could create this as an asterisk, it returns it. So I come up there and that's how I write it, right? Problem is that doesn't prevent me from writing it wrong. So yes, I can combine types, but I have to really be careful about that because to combine types, I need to cast them to some common type. Gnat has this concept that came in Ada 2012 called the dimension aspect. And what dimensions does is allow you to create this dimension system and then create types based on that dimension system. And I haven't gotten into, there's a lot more fields in here than these here, but we can sit there and say we have a mile type, a length, mile, which is using a length, hour, which is time, unit symbol is hours. And so what we have, this is the system we create. Now we create types based on that system. So we can have miles, which is of this system type, and we say, okay, it's mile on the top of the divisor, nothing else on the bottom. Hours is the same thing, but miles per hour puts a mile on the top, hour on the bottom, and that will label as miles per hour. So now when I create my speed function, it returns miles divided by hours. Cool, and that's valid because of the dimension system overriding it. If I make that mistake and say divide hours by miles, it's actually, now it's a compile error. I'm not casting the type back and forth, so it allows me to come up and enforce strong typing even when I have to combine types. Finally, from the coding standards, a lot of people don't do a lot of work with Pragma Pre-Elaborate, Pragma Pure. Pragma Pure is a way of saying that this package is really an operations package, possibly a types package. It does not, there's nothing happens outside of a function. There's no global data, no state changes happen during this inside of Pragma Pure. So I know any function in here, if I have math packages, those can be pure. Calculating a square root or whatever doesn't require me to change the state, and I know because it's a pure package that it's not going to be a pure state. It also provides some information to the linker, the binder, that says that a pure unit is allowed to be elaborated before anything else because we know it doesn't rely on any other state data. And because it only depends on any other pure units, that we know that even down the road, nothing else will be modified by calling a function within a pure unit. Coding techniques. This is one we learned at a customer site. It's called, I call it straight line branching. It's a name I made up. I don't know if it's valid. If you have states that you're constantly checking, you're in some code and you're going to say, If this is, if my state is valid, go on to the next step. And I keep going and keep going and keep going, all the way through however many steps I have. If I fail, I want to stop. But I could sit there and say just return. And we always use goto, and there was a discussion a little while ago about how valid goto is. I'm still on the, you should be able to write code to not use goto. This here is a way of getting past those type of things. So the way a customer had come up with this situation is what we call a single iteration loop. So if I do regular status checking, for those of you from the New England area, the storm comes, you got to go out and buy milk and bread. So the first thing you do is drive to the store. Did I get there safely? Yes. Okay, go buy the bread. I found the bread? Yep, go get the milk. Got the milk? Yep. Go ahead and pay for it. Everything good? Yep, return home. I finally return home, and I batten down the hatches. Now, if any of these states fail, I can't really do a return because I have to make sure I close the windows and all that stuff. And I don't really want to do a goto with a label because me personally, I don't like gotos. And if I get more and more states here, this is going to come off, even here we're indenting a lot. I'm going to keep indenting past the end of the screen. So if I wanted to do that with more states, I could do it with a single iteration loop. And all that does is say I'm going to go through the loop once because it's just a chunk of code, but now I have the ability to do an exit when. So if my state fails, I exit. My state fails, I exit. And whenever I exit the loop, I'm going to go batten down the hatches. So it allows us to write this straight line. I don't have all the indentation and all that. And it gives us that capability to jump out of a loop because it's not really a loop without having to write gotos or anything like that. One of the things that I found fascinating in talking to NVIDIA is a concept that, from my background, I've been much more involved in the avionics industry, embedded systems and all that type of stuff. And we're really looking at speed and size and all that type of stuff. And there are other companies out there, when we're talking about security, about secure applications, is that you write code differently. There are certain things that you need to do. Quentin had mentioned this yesterday when we were talking about a password algorithm. If I have a string and I'm trying to compare it to an algorithm, typically if I had a string trying to compare it to my base string, typically I'm going to look through character by character. Say if the first character is right, good. If the second character is right, good. Third character doesn't match, exit, I'm done, give up. Well, except if I'm looking to crack that, if I'm looking to break into hardened code, if I'm looking at execution time, I can tell by execution time which path is faster or shorter or longer, and therefore I can tell when I failed. In theory, I can tell when I failed the password match and try to figure out what the actual password is that way. So what we really need is a time constant loop. I need to be able to write code that says that I need to look in a group and look at the list and maintain the status. I need to know if I passed or failed, but I have to look at everything. I was thinking about it the other day watching TV. Magician, if they were, when they sit there and they say, hey, is your card in this deck of cards? They don't ask you, is it this one, because that kind of gives away the trick. But your job is to look at the whole deck and say, yes, it's in the deck. That's all I care about. I don't care where it is in the deck. So it's simple. This is what we would write in a normal search, right? If the entry, if I go through the loop, if the entry doesn't match, return false, otherwise return true. So if the password's 100 characters, I can return after the first, the 30th, or the 100th. And I know, but I'm going to go through that loop some n number of times, which is only determined by the entry value. If I want a time constant search, it's the same concept. I have to look at every entry in the range, but I never loop. Not only don't I loop, don't I ever exit? So the result is, well, did I find it before? If yes, and we're still good. Otherwise, we're going to return the false. Did I do that right? Yes. Okay. Sorry. Right. Because once that doesn't work, the result becomes false. Good. Even when you look at the things here, and versus and then, timing issues. And then is going to say, hey, if I found it sooner or later, I'm going to do less processing. This loop is going to do the exact same number of steps regardless of, to an extent, we're not going to go down the assembly level, but the exact same number of steps regardless of whether it ever fails or it passes at the first element or the last element. We always talk about modularity and writing code that's modular. One of the benefits of writing good code that's modular is the ability to anticipate code changes. Now, obviously, you can't predict what's happening, but if you write code in such a way that you can change the code without drastically re-architecting, then you've come up with a better way of writing your code. Send this, and I've got a simple requirement here. I'm going to write my code. It's going to install an interrupt handler. If an interrupt happens, I'm going to read your register and write it out to some log, some whatever. Easy enough, pretty simple. So I do this here. I say, okay, down here I install my interrupt handler. When I get my interrupt, I read a register and I print it out. And that's great, and that's going to do everything I want, provided I'm using VxWorks and I have text I/O capability. If I don't have those capabilities, I have to go in. If I want to report to a different system, I don't have file I/O anymore, different target, I have to go in and rewrite this code. And if I've done this through 10 or 20 or 1,000 different packages where I've interacted with the OS and the file system, that's a lot of code I have to change. If I write this in a modular method, expecting my things to change, if nothing changes, hey, that's fine, I've still written the code. But I come up with my own I/O package, my own hardware interface, my own registers package, and they're just wrappers, abstractions, if you will. Data abstractions, not ADA abstractions. So here, the interrupt handler just sits there and it reads the register, prints it out, however my I/O does it, sets an interrupt, basically passing in the address of the function. So if my I/O has access to text I/O, cool. The body of my I/O is fine. The interface is fine. The register's values are fine. All I have to do to modify my code is change, in this case, 3 package bodies. Now the code works the same as it is always is supposed to work, but I can switch targets, I can switch file systems, I can remove my file system, whatever I need. I don't have to go through and find all the code. I've noticed this a lot. Typically, it happens more in the C world. ADA people I think are more likely to create these abstractions because they're used to specs and bodies. But I noticed that, in previous life, every customer, every package had a pound include of VxWorks.h, which means every package there in still ADA. Every file had a pound include of VxWorks.h, which means if you change to a different target, you've got to change every single one of your source files. So writing code, thinking ahead, what happens if these things change? What happens if my register address changes? I'd go one step further. I just didn't have enough space to put it on the slides. I wouldn't even be using addresses here. I'd give registers names. And then the address on the register can change based on the name, based on the implementation. But I wanted to keep it short to fit on the slide. Debugging private and complex data. Sometimes you need to print an object. You're in the debugger, and I've got this record, and I want to print it out, and it's got 17 fields, and I say print, and it comes out, and I can't even read it. It scrolls off the screen. Tick image doesn't generally work because on private types or non-scalar types, just because the design of tick image. I have been told that 22x will help with that, but we're not there yet. So you can't do a tick image typically on a record or on a private type. And even if you could, it's just going to print it out in its own format. The whole Python print, a print a list will print it however it wants to print it. Using our modularity here, we can create child packages. If I have a types package and it has some types in it that I want to print, I can create a child package for that parent. And in that I can have image functions or whatever allows me to do a pretty print. I can pass in parameters, whatever. And the benefit of the child package is the child package has visibility to everything in the package spec, which allows me even private types. And I don't have to with it in. I can create a debug test, a test driver that withs in the private package, but it can be part of my actual underlying software, but not ever compiled into my deliverable. So by using child packages, I have access. I can use pretty print functions. I have this private types package. I have an employee, creates an employee, and here's my record. Again, simplifying it for space here. So if I wanted to print that out, yeah, I could print each individual field, but maybe I want to print in the debugger. I'd say I hit a breakpoint. I need to print something out. In my debugs package, I have a bunch of all these functions that I don't care what the type is. The body of that debug function is going to return the appropriate text. And now I can look at it pretty. Maybe there's all sorts of fields in there that I don't care about because they're not used in my application or I'm not crashing on that. So I can change this for test purposes however I need. And this package here is never delivered as part of your actual product unless you've left it a with in it somewhere in your code. Trick I learned some years ago. We just talked about pure units and not having side effects. That's mostly true. If you want to do debug information out of a pure unit, coverage could be one of them. I need to call text.io from my pure unit. I can't call text.io. Text.io has side effects. I can't have side effects from a pure unit. Okay? You can cheat. The Ada language the Ada compiler does not verify imports into a pure unit. So you create your own debug unit that can still be pure, and it does an import of text.io or whatever else you need. So we've created a function here, which just a simple using puts, and I use puts just because with Gnat we at least have a visibility to the C runtime library. If not, you can create your own. But once you create it, so here's my debug thing here. Procedure print. Procedures don't have side effects because it's a pure unit. I can print it out. The compiler doesn't care. I've printed out and I have debug information from my pure unit. Helpful for a lot of times when you're doing calculations, especially in math packages, if you're writing your own functions, it allows you to see what's going on in those particular functions without having to necessarily step through the debugger. And here, so here I have a function, a pure function. I can do a print. It didn't matter what happened in here. As I forgot to put the print in there. But again, the same type of thing, an exception. Hey, I got the exception. That's why I failed within that pure unit. Other functionality within the language itself that helps you in debugging. Normalized scalars is a way of telling the compiler every object that we create, I want initialized with something that shouldn't fit in the range. It should be an invalid value. So that if I ever do a read of an object before I've done a write to it, I should get a failure. The other way to do that is run it on Windows, because Windows always finds those things for you. But it applies normalized scalars. It's going to take any uninitialized object, set it to something that's hopefully out of range. If you're using only a certain number of bits, it will set the object the bits that aren't being used. If the type has a range constraint, it will set it outside of the constraints. And then when you're running hopefully your tests as opposed to delivering your code, it increases likelihood of finding these problems. The issue with Ada is everything tends to be if you're not on a target, everything tends to be initialized to 0, which is fine because 0 tends to be valid for most types. If it's not valid, obviously you're going to find those quickly. But if you have an integer that goes 0 to 10 and you read it and it's defaulted to 0, that's not going to fail. But if you read it and it was never set with normalized scalars, you should get typically will get a constraint error because it's out of range. Similar to initialized scalars is the Gnat Pragma called initialized scalars. It's similar in that it allows you to initialize global data. It's different in that normalized scalars is for your compilation, your environment, your whole executable. Initialized scalars is for a particular package. So you can initialize it on a particular package. Initialized scalars also allows you to set different initialization values for different types. Shorts can have different than longs, floats can have different than booleans or whatever it's necessary. It's not a default. And you turn on the validity checking with Gnat V, and you'll see all those errors if you've ever done a read before a write. And finally, the first debugging technique that I was ever taught is called rubber duck debugging. I heard the phrase, and I actually, in doing these slides, I worked with it. It's actually a documented term, and there's I thought I was going to put the link in there, but there's a book that talked about programming that identifies this as rubber duck debugging. I was told it wasn't told as rubber duck. I learned that term a long time ago. But the best way to figure out why something doesn't work is explain to somebody else why it should. I say program A does this, and then it does this, and then it's, oh, wait a minute, that's not right, and I can go back to my desk and figure it out. And the benefits, the reason it's called rubber duck debugging is you're not looking for input. You're looking for a sounding board. So you're talking it out loud is what actually triggered the diagnosis. So it doesn't need to be a person. It can be your rubber duck. The final thing here is, and I've been talking to a couple of people here about coding and all this stuff. Rubber duck debugging is what we used to call desk checking. Look through your code. Yes, your code is supposed to do what you wrote it to do. If it doesn't, that's not because it doesn't like you. It's because you did something wrong and you can't see it. So step through it. I do this all the time. I write, I'm going through a loop. I write a little table that says this is my index, this is my position, this is the array I'm looking at. So one of the best techniques of debugging is rubber duck debugging. Understand what your code is supposed to do, and then you can figure out why it's not doing what you asked it to do.